Measurements are always challenging, but this is particularly the case in granular materials and soils, because pretty much everything that we want to do to determine a property actually affects the property that we are trying to measure. This is a following from thermodynamics. The measurement always alters the measurand, but as I said, this is particularly the case in soils. Today we're going to look at stiffness in soils. And this is an example of the profound differences between what you want to measure, what you measured, and what you think you measured. Let's see. As a starting point, we could think of a few examples. Case one, if we look at our weight, it changes during the day, it goes up and down, and during the week, but it follows a trajectory throughout the years. We are either increasing or losing weight. There is an overall trajectory with oscillations. So now we could think of what is the local rate of change of the weight or the global rate of change of my weight. Similar distinctions occur when you have a mass and a spring. This is a mass, we are pulling with a spring, and we measure the force and the displacement. When we graph force versus displacement, now it may go up until we exceed the Coulombian friction, but because the static friction is slightly higher than dynamic friction, it may jump, and then it goes up again and jump, goes up again and jump. So if I look at the overall trajectory when this becomes really small in a large experiment, then I have something that probably looks as like that, where all these small oscillations will be locked in within the curve, hidden in that curve. Imagine now that in a soil you have thousands, millions, billions of particles every time you run a triaxial test or a consolidation test. And so what is really happening is that certain groups of particles slip, and then there is a little bit of a domino effect transferring loads to neighboring groups of particles, and then the next one slips, etc. In the overall picture, we see kind of a smooth curve, but in reality, that is the integral of so many local slippages. And so let's take a case in point. Let's say that we're going to run a triaxial test, and let's say that we are going to start with a tau sigma space, and the soil begins and with an anisotropic state of stress, where this is sigma z, and this is k naught sigma z, and of course all this is in effective stress. Now if I begin doing axial compression, this begins expanding until it goes to the failure line. If this is phi, I have to go back and draw the circle to see where the failure will take place, and that is the amount of deviatoric load that this sediment was able to take. Now, typically, we don't have much resolution when we make the measurements, particularly if you look at all data that was done with dial gauges. Nowadays, we have continuous sampling, or sampling, nothing is continuous, sampling with very small delta t's. But we are going to see something that looks like that, where this is sigma deviatoric versus strain. Now, let's say that we fit, this looks like a hyperbolic model, so let's fit the hyperbolic model that you will find in other videos, and from the hyperbolic model, I'm going to get the two very important asymptotes, which is the asymptote at the smallest strain and the asymptote at largest strain, which is the strength. Now, given the fact that that is a continuous function, I can compute the derivative without the noise of experimental errors. And what I'm going to get in this case is that the stiffness, and that I compute as delta sigma d epsilon, that stiffness, let's call that the tangent stiffness, is going to, as you can see, it goes to 0 as it approaches failure in this case, and so starts at a fairly high value and then it drops. And in this case, I'm plotting E tangent versus strain. This is the deviatoric strain, the shortening of the specimen divided the initial length. Now, as I was running the test, I could have simultaneously sent a very small perturbation. In other words, a shear wave, most likely. If the soil is saturated, I want to know how the skeleton feels. I'm going to use shear waves. So this specimen will have not only the vertical deformation and the stress, but it will also have some type of crystal, probably bender elements, to send shear waves across the specimen. Now with the shear wave, I'm measuring the shear modulus. I can infer Poisson's ratio. As you remember, it's always very small, in the order of 0.15 for a small strain. So I can compute the Young's modulus. And if I do that, you will see that the Young's modulus, let's say that I measure at a specific instance, the Young modulus goes like that. So this is the modulus obtained from shear wave velocity, which is a small strain modulus. And the small strain modulus hardly decreases at all. In fact, in some cases, we have seen data where the small strain modulus, in other words, the shear wave velocity, increases as we are approaching failure. Not if the soil had an initial cementation, but it does happen in many other soils. Conclusions. The tangent modulus computed from a monotonic loading curve is very different than the small strain stiffness measured instantaneously at specific points along the path. And by the way, I'm plotting here, to be precise, in logarithmic scale, and this one also in logarithmic scale, so I can actually magnify these changes. But then we have to think, what is the value of small strain measurements? And the value of a small strain measurement is to obtain this initial value of a stiffness, and particularly when we do that measurement in situ without ever sampling, so we don't disturb the diagenesis of the sediment, that is a very important value because it locks in this asymptote of the stress-strain curve. But at any other point, it becomes a misleading parameter. This is like observing our change in our weight between the morning and the evening compared to the overall trend of our weight, or the same as we did with the mass and spring. So indeed, the small strain stiffness measured with wave propagation is different than the tangent stiffness computed from monotonic loading. Said in other words, the small strain stiffness is an assessment of a state at that precise moment. It's checking how the contacts are and how stiff those contacts are. The tangent to the low deformation curve is giving us a rate of change of the fabric in this case. How is the soil evolving? It's a rate of change. This one is an instantaneous measurement. Now, in many cases, we do similar measurements with odometer cells. And this becomes even trickier. And let's say that in an odometer cell, once again, just to be complete, I'm going to put here tau sigma, and we're following the K0 line. So this is the friction angle, and this is the K0 line. And so as we increase, not only the vertical load, the horizontal load increases in such a way that they define this line, which is the K0 line. And you can compute it readily. Now, what happens in this case? Well, in this case, now, instead of plotting a stress versus a strain, we're going to plot the evolution of void ratio with respect to the applied vertical stress. And as you may remember, these curves are quite exponentially decreasing from a void ratio E0 at 0 effective stress to a void ratio E infinite at an infinite effective stress. So this is pretty much the shape of these curves. And you can use any of the asymptotically correct models to fit actual experimental data that you're going to gather. And now, from this curve, we can compute the constraint modulus, because the change in void ratio divided by the initial void ratio is the strain, and the change in stress gives us the change in stress over change in the void ratio. In this case, is the constraint modulus, 0 lateral strain. And when we do that now, we're going to plot the evolution of the constraint modulus measure from the tangent of this curve with respect to, let's plot versus the applied stress. And these curves tend to look something like this in a log-log scale. I'm going to paste data at the end of this presentation so you can actually see actual data. Now, once again, our odometer cell could have had bender elements built in, so we can measure the evolution of shear wave velocity. From the shear wave, we get the shear modulus. From the shear modulus and Poisson's ratio, once again, 0.15. You can compute the constraint modulus from theory of elasticity. And when we do that, this data appears somewhere like that. So this is the constraint modulus, tangent, and this is the constraint modulus computed from small strain measurements. And the difference here can be quite pronounced. There could be easily 2 orders of magnitude here. So this can range from 10 to 1,000 times. And you have to wonder why. And well, one of the reasons is that the odometer is a wonderful test, but it's really subjected to lots of problems at the boundaries. So when you look in detail, the odometer cell, the surface of the soil is probably something like that. And so when we plate the porous stone, we have to squeeze all that gap, particularly at low stresses. So we're going to have a significant gap. And the same will happen with the lower boundary. So lots of local deformations. Furthermore, on the boundaries, there are also gaps that as the soil squeezes sideways, it has to fill in, etc. It's a difficult situation. With triaxial test, we can avoid that, the sitting effects, by putting, for example, local displacement transducers. And we measure locally rather than measuring the boundary effects. We cannot do that in an odometer cell. But once again, the take-home message is the tangent to the void ratio stress curve is completely different than the small strain constraint modulus that you would measure instantaneously with wave propagation. This is, wave propagation gives us an instantaneous measurement, while the continuous curves are giving us a rate of change. 2 completely different physical interpretations of these measurements. Probably the take-home message is always to remain very alert as to what we measure, what we want to measure, and what we thought we measured.